Okay, hi everybody. Sorry. Um, I was just excited that my camera was working the first time I plugged it in. Sorry. And the microphone's working. All right, good afternoon, everybody. Um, we are going to learn about space-time cubes today and pick up where we left off from last time. So, hope you guys are doing great, and we'll motor through this as efficiently as we can. Ask me questions in the comments if you have any, and we'll try to get through this as efficiently as we can. So maybe we can get out a little early today and go enjoy this fine fall day. All right, let's do it. Okay, so last time we were looking at the application of a tool that allows you to calculate density of points, and or if the data has values associated with it, you can feed those values into the analysis as well. But we were just using it to look at the density of burglary and robbery events that happened in Philadelphia during the month of January in 2014. So this is what the burglary map looked like. So we got some locations where burglaries are more happening more frequently, spatially more dense, and robberies. And it's hard to see because it's mostly transparent. And we noticed this interesting neighborhood where there were a lot of burglaries, but not many robberies. Burglaries, robberies, burglaries, robberies. So over here, this is a location over there. It looks like they're here in the middle of Philadelphia. A lot of robbery, but not as much burglary. And then there's a burglary hotspot down here. So it's interesting. You know, you can imagine the usefulness of a tool like this for police for police work. All right, so let's turn off all these layers, except for we'll turn back on the burglary layer. Oh, I still have a lot of stuff selected. Let me clear my selection. Okay. And so just the burglary layers on. And so let's take let's use another tool to show a different way of visualizing this burglary data. And no, let's not do burglary. Let's do robbery. All right. So we use another tool to visualize this robbery data, and it's called a hotspot analysis. And oh, my cat. Hey, Clemmy. Hotspot analysis is the result that we'll get will be similar in some ways to the kernel density analysis, but the hotspot analysis actually carries out some statistical analysis, and the null hypothesis. Well, when you're doing statistics, inferential statistics, you want to be able to draw a conclusion. Excuse me, Clemmy, knock it off. Cats, they're possessed. You want to be able to make draw some conclusions from your data, and in inferential statistics, it involves a hypothesis, and the null hypothesis that you would have for this situation is that you have events that are uniformly distributed spatially, so there's no patterns, there's no spatial patterns whatsoever, and so this hotspot analysis tool will detect regions, if they exist, where there's a statistically significant cluster of events or statistically significant absence of events in your data set. So we'll apply this tool, this hotspot analysis tool, to the robbery data, and then we'll take a look at the results and talk about what we're seeing. And let's do it. All right, so let's find the tool. It's probably up here. Here, it's right here. Here it is. Optimized hotspot analysis. It's up here in my ribbon as well. There we go. All right, so my input features are going to be robbery, all the robbery data, just not just January, and the output will be optimized hotspot analysis. Let's make that a little shorter. OHSA. My analysis field will be, well, I'm just going to leave these this blank. We want to look at the count, the frequency of the points spatially. So we'll leave that blank and leave this as the default, and we'll run it. This shouldn't take too long to run. And we're there. All right, so I'm going to turn off we can't see what's going on because the robbery stuff is still on, so I'll turn it off, and then this is what we get. So, oh, I still have my swipe tool on. Sorry, I'm trying to. Here it is. Okay. So this is what we get, and so this is a. Let's look at the attribute table, because what we have here are actually this is a feature class made of polygons, and as you can see here, it's polygon shapes. So that's different than the density kernel density analysis that gave us a raster output. We have polygons, and each of these polygons has attributes associated with it. And here, let's close this, and let's zoom in here, and I'll click on if you look at here, you got red spots, blue spots, and then just kind of like white color polygons. And so what we're seeing here are maybe if I turn the robbery data on, you can infer what the red spots mean and what the blue spots mean. You look at the legend over here, and you see red spots are called hotspots, and the different shades of red are different levels of confidence, and the blue colors are cold spots with different levels of confidence. So let me click on one of these things, and its values pop up. So this is a block. Let's do something. Whoa. Ooh, keep clicking. There we go. Let's do it this way. So I click a block right here, and you can see it's selected right here. And then I'm viewing the attributes over here on the side associated with this feature that I've selected. So what we have here is a square, a block where there were 13 incidents that occurred and were assigned to this block. And these two values right here, one's called GIZ score and one's called GIP value. So these are the values that are associated with the hypothesis testing that's determining that this is a hotspot. And so the way this works is Maybe I'll try to find you a picture. Good old statistics. Z-score. Zoom out. There we go. Okay. So this will work. So what we're looking at here, this is a normal distribution, and a normal distribution is a distribution that describes a random variable that obeys the normal distribution and that are normally distributed. So what that means is that you would expect, let's say you were picking numbers at random according to this distribution. Most of the numbers you picked would be close to 0. Some of the numbers would be 1 standard deviation away. Fewer numbers that were randomly drawn would be 2 standard deviations away, 3 standard deviations, 4 standard deviations away. So it becomes, when you're drawing numbers from a normal distribution, it becomes increasingly unlikely that you're going to get really big numbers or really small numbers. And so the z-score is, think of it as like a normalized measure of standard deviation. It's, well, you can think of it as the number of standard deviations that you are away from the mean of a distribution. So if you think of this robbery data, there's a certain number of events in this geographic location, and so you could figure out, well, what is the average number of events in a given region? And then you could look at each of your blocks and say, are the number of events that are in that block statistically speaking different than that average? And that's what it's showing here. And the values that you're getting here for the z-score is saying that this is essentially, there's the likelihood of you just randomly having a spot here with this many robberies is 8 standard deviations away from the mean. So that's exceedingly unlikely. And the p-value is the probability of that just happening randomly. And you see the p-value is 0. So it's basically saying there's essentially 0 probability that the number of robberies that occurred in this spot would happen by chance. And so that's what makes it a hot spot. Statistically speaking, there's more robberies in this spot than would happen by chance. And out here it's the same thing. Statistically speaking, there's fewer robberies that happen in this spot than you would expect by chance. So there's more of a discussion in the textbook. There's more of a discussion of the normal distribution and a z-score and a p-value. So it's worth reading through. All right, but now the time you've been waiting for. Let's create what's called a space-time cube. Okay, so we'll turn this off, this hotspot analysis off, and let's go to the tool, geoprocessing toolbox, and let's search for this function. What we want to do is we want to create a space-time cube. Let's see if we can find it. Create space-time cube by aggregating points. This tool right here. So we'll pick that. Our input features are the robbery data, and let's make the output robbery space-time cube STC. Let's give it the file extension NC. That's important. That's the type of data set that's going to be generated here. It's called a network common data form. Network common data form. And we got to put that extension on there so that it knows that that's the file format we want. All right, what else do we want to do? The So space-time cube implies that there's going to be a spatial dimension to our results, but also a temporal dimension. And if you remember in the attribute table, one of the dimensions, one of the fields is dispatch date. And we're going to then aggregate our data into time slices that are each 1 month in duration. So what it'll do is it'll look through our data and it'll aggregate all the data in a given month and create a bin for the data for that month. Fishnut grid, yeah, that's good. Okay, we'll keep the rest of the defaults here and run it. And let's see. Wow, that didn't take very long. So spacetime cube by aggregating points completed with warnings. Let's take a look. Let's view the details. It says the default distance interval is 992 feet. Alright, I'm not sure that's a warning, but okay. Let's see if there's any messages. Did it give us any messages? So this is interesting. It's telling us what it did. It says, you guys probably can't see that. I'll read it to you. It says the space-time cube has aggregated 7,006 points into 9,200 fishnet grid locations over 12 time step intervals. 12 time steps because remember this was for 1 year and there's 12 months and we aggregated by a month. Each of these grid locations is 929 by 929 feet. The entire space-time cube spans an area of bloody by bloody. It's not that important. Each of the time step intervals is 1 month in duration, so the entire time period covered by the space-time cube is 12 months. Of the 9,200 total locations, 1,904, 21% of them, contained at least 1 point, 1 robbery, for at least 1 time step interval, 1 month. These 1,904 locations comprise 22,848 space-time bins, of which 5,618 have point counts greater than 0. There is a statistically significant increase in point counts over time. Well, that last bit's the most interesting thing here. There's a statistically significant increase in point counts over time. So that's saying that there's a trend that as you go from January, February, March, April, May, June, July, August, September, October, November, December, the number of points, the number of the points here represent robberies is increasing over time. All right, well, that's all well and good, but you know what's neat is being able to visualize the results of this space-time cube. And in order to do that, we're going to do it in 3D. And we haven't done this before. So let's see if we can make it work. All right, we want to insert a new map, and we want this map to be a new local scene. So we're going to do that. All right, and what we're going to want to do is, it's a good way to explain this. We're going to want to visualize these little bins in our space. Think of the space-time cube as this giant cube that has, did you ever see that horror film, The Cube? It's nothing like that. But it's a cube of, it's like a giant Rubik's cube, and it's like a cube of cubes, and each cube represents each cube of cubes, and each cube represents a specific spatial location. Remember, it figured out automatically a good value to use, and it said that each of these cubes is a 929 by 929 foot section of the city of Philadelphia. So each cube represents the count, the number of robberies that occurred in that location for a given month, and then you got 12 cubes stacked on top of one another, one for each month. So we want to visualize it to kind of like, show these cubes. And all right, so that means it's sort of like, you think about mapping, typically elevation is what you plot on the vertical axis, but here we're going to plot time coming out of the map instead of elevation. All right, so we're going to get rid of the default elevation surface, which is part of our scene here, and then proceed. Oops. All right. So here it is, this elevation surface that is here. We're going to delete that, remove that. All right, and we are then going to go to the geoprocessing pane, and we're going to search for visualize space-time cube in here it is, in 3D. Okay. So now I got to find my space-time cube. There it is, robbery space-time cube. I saved it in my project directory. The cube variable initially here is just going to be the count. It's the number of robberies that occurred in each of these cube, in each of these squares in each of the months. And we'll make the output space-time cube 3D. Let's run it, see if this works for us. So let's just put it on the map automatically. It says it completed with errors, or with warnings. Let's view the details. The time it takes to render the cube in 3 dimensions may vary considerably based on the number of features in the graphic card associated with your CPU. If some of all the data is not drawing, it may fall outside of the visibility range limits, which can be cleared, yada yada yada. Okay. Well, now we get to see no, zoom in, zoom in. I figured this would be faster on my computer. I have maybe my wonder if my GPU is being leveraged here. Oh shoot. I just forgot how to make my perspective change. Darn it. Hold on. I forget how to do this. Wonder if I do zoom to layer, if that will work. That worked all right. Okay. So what you're seeing here, wish I could, how can I tilt this more? Hold on a second. Oh shoot, I keep rolling my mouse the wrong way. Alright, well I guess I won't worry about it. I was trying to... We can zoom in here. Maybe we can see. I think if I change the base map, this will be a little bit easier to see. Or not. How about imagery? It's a little bit better. So you zoom in here, what you see is you see all these cubes. So each spatial location has a cube, and you can mess with the visualization and how it looks, the colors that are used. But where you see this stack of cubes, there's a cube. You can zoom in on one of these. How about right here? So at this spatial location, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 cubes. One for each month. And it looks like this last cube has a count in it. So it doesn't look like, some of these look like they're zeros. And yeah, count 0. So this cube doesn't have any robbery counts in it, but this cube right here, it has 1, and this cube right here, that was a busy month at that location. There were, oh, wrong one. There were 4 robberies at that location in that month, July. So what you're seeing here is all the data, but it's splayed out by month. And where you see purple, that means that there was a robbery in that month. So each slice here, another way of saying this, is each level of this stack of cubes represents data from a different month. And if there was a robbery at that location in that month, then you're going to see purple color. And the darker the purple, the more robberies that you're going to see. And it's actually a 3D thing. You see that? Okay. All right, let's see. What's next? Sorry, I'm just playing with the navigation tools. I haven't played around with space-time cubes very much. You can turn that off and on. Okay. So what's next? So you can also run hotspot analysis. This is, so what we have here is kind of like the kernel density map, but we're splaying out the data for various months, and you can go through each of these slices separately and visualize them one at a time. And you can even create animations that show the slices of this space-time cube sequentially. And then you can visualize this another way. So we just visualize the count, but we can also visualize trends using hotspot analysis. So let's do that. So we'll come back out of the 3D scene back here to the 2D map, and let's go to the geoprocessing toolbar, and we're going to use this space-time cube data to calculate something called an emerging hotspot. See if we can find it. There it is, emerging hotspot analysis. Okay, and our input time cube is going to be the same, and our analysis variables count, and we'll do the output as emerging hotspot analysis in the same thing. And we'll keep the rest of the default parameters set as they are, and we'll run it. All right, so then we get a map that looks like this. So this looks sort of like the hotspot analysis for earlier, but look at the legend here. Look at all these symbols here. So that here, this tool is doing an analysis, a statistical analysis on the data in the space-time cube. And so it's looking at each of these stacks of cubes and it's looking for trends spatially. So it's looking for patterns spatially, but it's also looking for patterns temporally. So it's looking for patterns in a given slice across cubes, but it's also looking for patterns vertically on the stack of cubes. So what you can find are, instead of just finding like hotspots, places where there's a statistically significant more robberies or statistically significant fewer robberies, you can actually tell whether the robberies are increasing or decreasing over time. So we look at some of these categories. Close that up. Close this up. So this symbol right here represents intensifying hotspot. What's an intensifying hotspot? Well, let's look at the trend. Min count, max count, mean, standard deviation. So it's a statistically significant, got a small p-value, statistically significant trend of increasing frequency of robberies in that spot. The solid red, they're called persistent hotspots. So those are hotspots where there's statistically significant more robberies and the trend is constant over time. It's persistent. There's even a category for oscillating hotspot. That's crazy. So locations where there's a periodic pattern. These symbols up here are new hotspots. So those are locations that at the beginning of the year were not hotspots, statistically significant hotspots, but by the end of the year were statistically significant hotspots. Do we have any diminishing hotspots? I don't see a single diminishing hotspot. That would be a location where there's statistically fewer crimes at the end of the year than the beginning of the year. I don't see any oscillating hotspots either. These symbols right here, that represents a sporadic hotspot. So that's a place that's hotspot some months but not others, and there's no statistically significant trend in the data. I mean, there's a lot of information here, and of course there's information about the cold spots too. So these are new cold spots, places where, and here you have emerging or persisting cold spots and sporadic cold spots, statistically fewer robberies over the course of the year. So, you know, this region in here is interesting because you have these regions of persistent hotspots for robberies, and it's surrounded by this cluster of intensifying hotspot. So these are locations where robberies are more frequent and the frequency is increasing. And then you got this block down here of consecutive hotspots. So that's a place where there were hotspots in multiple months consecutively. And then you got some new hotspots popping up. And down here, you know, so you can see patterns in the crime frequency, and it appears that the hotspots, the locations of crimes, are expanding. So there's this spatial spread of robbery hotspots as you go out throughout the year. You have this region of sporadic hotspots, and then there's all these new hotspots emerging on the periphery. So the crime is spreading. All right. So let's see. Oops, sorry. Let's do one more space-time. Nah, let's not do that. Okay, we could also visualize what's happening here in a space-time cube. And maybe we'll save that for next week. Well, let's do it. Let's do it. All right. Make sure I keep grabbing the wrong mouse. So let's go here and let's turn off this layer, and let's run the visualize space-time cube again. So we'll visualize the space-time cube that we made earlier, and we'll do count, but now instead of doing value, we're gonna show hot and cold spot results, and we'll call this give it a new name. So now instead of just looking at the counts in the fields, we can look at hot and cold spots. So you can look at the evolution of, like down here, you make this a little bit transparent. Too much. Oops. You remember down here, did I turn it off? We had all these new hotspots down here in this southern region, and you can see that that's happening, that early in the year there's no hotspots, and then later in the year there are. So you see this temporal evolution of the dynamics of these robberies occurring in this location. So let's see, intensifying hotspots here in the center of our map. Let's see if we can find those. This is like just too much to take in, but what you would see in an intensifying hotspot is you see a hotspot that gets hotter as the year goes on. So you start out red and it gets redder as the year goes on. These sporadic hotspots, what you should see is data that, up here, where you have some months that location's a hotspot and some months it isn't. And there's no statistically significant trend in the way that happens. And persistent hotspots, see if you can see those. That would be this region in here where you get hotspot, and it's a hotspot the entire time throughout the entire year. So it's another way you can visualize. So this is using the same tool, visualize space-time cube in 3D, but instead of picking the value display theme, which just shows the counts in each of these boxes, it's showing hot and cold spot analysis results. All right. So there's more in your textbook about exploring data in 3D, including making animations, and I mean, it's neat stuff, but I don't think it's really that important when you're just learning GIS to be able to show your data in 3D. So maybe we'll come back to it if we get a chance and play around with this a little bit more and maybe create an animation of our data. But definitely the focus of this course is analyzing data and presenting it in 2D, flat maps, using colors and creative symbology to tell your story. Instead of, I feel like when I look at these these visualizations of these time cubes, that it's just, it's flashy, but it's pretty overwhelming too. And I guess it's better to look at this kind of data in a dynamic way where you can zoom in, zoom out, move around. Looking at data this way on a static map, it might work in some situations, but it just seems to be overwhelming. It just seems to be harder to see. There's too much information. It just overloads my brain when I look at the screen. Definitely interesting and definitely neat and impressive to look at, but I don't know if it's really of much utility for telling a story often. Okay, gang, so we'll stop there for today, and we're going to work on Chapter 9, material from Chapter 9 next week, and my goal over the weekend is to finalize the assignment for Practical 2, and I'm formulating the parameters of your end of semester project, and I'd like to get that to you as soon as you can so you can start brainstorming and thinking about narrowing down your theme for that as well. Okay, gang, well, you guys have a good weekend, and